Cheers, everyone. Cheers, everyone. My talk is called Cursed Things to Do with Lambda Functions. And I typically give a lot of talks around what makes good practice, what's good exaptive practice from other areas that I've worked in. And so this was a really fun talk to put together because it's, from the point of a villain, like what is the worst things we can do with Lambda functions? What does Lambda technically allow us to do that may not be best practice? So to start off with, I just wanted to thank all of the sponsors. I don't get to subject people to my cloud opinions often enough, but thanks to all of these sponsors, I do. And specifically to the room sponsor, Software One, really appreciate it. And yeah, go and check out all the sponsors' booths as well. They're all over on the terrace, so yeah, make sure you check them out over lunch or any of the breaks. So who am I? I'm a lead consultant at Cognizant. Not Cognizant Server anymore, we're just Cognizant. But I'm a cloud native and software and security specialist. And from a consulting lens, I guess all you need to be a software consultant is pretty much you just need to know the words, it depends. That doesn't look right, and you probably don't need Kubernetes. I have lots of opinions, and hopefully some of them are right, or at least useful. I'm hoping the Venn diagram between this talk and the ones I have that are actually useful is close to a circle. And I'm also a low-level programming language enthusiast. So I come from an embedded IoT background, so my first love was always C. There's exciting stuff happening in that space, but I won't get too bogged down into that right now. So the concept behind this talk, why do we care about doing things badly in Lambda, right? And we care about doing things badly because by testing the bounds of a system, we build mechanical sympathy. And so it was a term originally from racing, mechanical sympathy, right? Like you don't need to know how a car works to drive a car, right? But understanding how a car operates makes you a better driver. So that's what we're going to do today, but instead of driving race cars, we are going to be driving Lambda functions. And so this might sound like this talk is going to be really boring now, right? Like how far can we push Lambda with hello world? And so that was the concept that I started with. And I wanted to see how far we could take this. And so we're going to use a very simple use case, but we're going to use that simple use case to do some fairly complex stuff. And AWS Lambda is less constrained than you might think, right? So we normally think of Lambda as this service that we bundle our code up into. We've got a very constrained runtime. It only has a couple of different languages that you can run on it. It's usually a certain version, all of that sort of stuff. But there's actually a lot more leeway than you might initially think. So the first model we're going to look at for Lambda functions is this. AWS sends a request to our code processes that request, and returns a response to AWS, right? And so very simple model. And to illustrate this, we're just going to use a very simple hello world function, right? And this is probably about as simple as it's going to get today. We receive an event, and then we return just a JSON object that has our status code 200 and a body with another JSON object of message, hello, and whatever the name was that was passed into the event, right? So let's prove out that model. Which way is my AWS console? Here it is. Now, I didn't record my demos, so fingers crossed they all work. So here we go. We've got our function in here. I might try and make that a little bit bigger. Same function we had before. I've got a test event defined. I can test that event, and it'll say hello test, because my name in my event body was test. So, okay, basic model works, right? Lambda is operating as we expect Lambda to operate. But I haven't actually been entirely honest, right? That model is probably a little too simplistic, right? That's not what we're here for. So what we're going to look at is this, right? So what actually goes on behind the scenes is Lambda instantiates a container. That container contains a runtime, which is something provided by AWS, right? And then that runtime is what actually interfaces with our code. So on the Lambda side, all Lambda does is start a container and host an API. And that API contains endpoints to get the next event and an endpoint to post a response back from our Lambda, right? But we don't see that API at all. The Lambda runtime abstracts all of that away from us. Our code just receives an event and returns a response. So this is what's actually going on under the hood, right? And if we dive into that a little bit. If it's just an API, right, why do we need the runtime at all? Why can't we just interact with an API directly? And so that brings us to our first cursed Lambda function, which is lambda.sh. So you've probably all heard that you can actually write a Lambda function in Bash. I'm not sure how many of you have actually gone and done this, but it is something you can go and do. So what we're going to do is we're going to instantiate a container. Our container is going to contain a Bash script. There's no runtime. Instead, we're just going to call the next endpoint to get our next event, and then we're going to do some processing in Bash and return a response. So what that looks like is something like this, which is kind of awful because we're interacting with APIs in Bash and it's never fun. So down the bottom, we've got all of our stuff. That is our loop to continually keep pulling the API for additional events. And then when we do get an event, all we do is we call our handler function up the top. We get our event data, and then I've actually got a Lambda layer in here which contains JQ. Does everyone know what JQ is? Yeah, it's just a Java JSON processing library that you can use from Bash, which is really handy. And all we do is we check if our event has a property name, and if it does have a property name, then we return the name, else we return world. So exactly the same thing we had before, but now in Bash. So, hold on, I think the next slide is, yes, let's prove our model. Exactly the same thing that we had for the original one. So we go into Bash hello world. I'm unlikely to get as much nice stuff in here, but, there we go. If we test this, I've got a test event configured. I did test this before I came in as well. And we can see I've added my name in, so our response is hello Aiden. I didn't return a JSON object just because I was lazy, but yeah, we can do exactly the same thing and get very similar sorts of response from a Bash Java Lambda function. So this is actually how custom runtimes work under the hood. So if you've ever run a custom runtime for Lambda functions, all they're doing is talking to the API, calling your code, and then returning the response back to that same API. Whoop. So this is really great for legacy code that can interact with HTTP that maybe doesn't actually have an implementation of Lambda. So you can spin up a container, you can put your legacy code in it, and you can write a thin wrapper around it in order to actually make it compatible with Lambda and interact with the broader AWS ecosystem. And that's all well and good, right? But I haven't shown you how to do anything that really breaks the mold yet, right? All we're doing is stuff that you can do in Bash or stuff in custom runtimes. But what if you still need to use Node.js, right? You're not going to start a container that has Node.js in it because, one, that's probably going to be inefficient, and two, it's going to be a massive container. So that brings us to curse 2, which is breaking the mold with wrapper scripts. So I haven't actually been entirely honest. We're going to refine our model a little bit more, right? And our new model looks like this. It's pretty much exactly the same. We instantiate our container, but now, right up the top of our container, we have our wrapper script. And then that's going to instantiate our runtime, and our runtime is what is going to call our code. So this is for when node options isn't enough, right? So there's certain things in AWS that you can put in node options. There's certain things you can't. And I do have a demo lined up for this, but in the space of me writing this talk and actually giving this talk, AWS has actually made it so the flag that I'm going to use as an example can actually be used in node options. But 3 weeks ago when I wrote it, it wasn't. But that's the benefit of working in cloud, right? There's always updates and always new stuff to try out. So here is our wrapper script, right? All I want to do is expose the garbage collector to my Node.js Lambda function. So all I do is I've got the existing args. I take the extra args, which is just our exposed GC, and then I insert the extra options into the call that instantiates the runtime, and then we can execute the runtime, right? So of course, 3 weeks ago, you weren't able to do this through using the node options environment variable, but you were able to use it from doing a wrapper script. So sort of AWS doesn't let you, but you still can sort of do it. Now, they let everyone do it. So then, in our handler, what we can do is we can then call those garbage collection functions, such as global.gc, and run the garbage collector on demand. So let's try that out, right? So we've got our garbage collected hello world function. And pretty much exactly the same thing as our first model that we proved out, except now we have global.gc being called. And so we can test this, and hopefully we get a response back. And it's hello garbage collector. There we go. And if we test this a couple of times, we'll see that GC is actually run every time. So we're getting 125 milliseconds in terms of our execution time, which is a lot slower than we would on our base Lambda function. So if we go back to our original Lambda function and start that test again, we'd expect this to execute much faster because we're not running the garbage collector every time. Maybe every fifth one might be a little bit slower. Let me just run that again, just so we make sure we've got a fresh container. Oh no, it's about the same time. Okay, well normally when you run it, maybe it's, yeah, I'm not sure what's causing that, but yeah, normally it'll execute in a couple of milliseconds on the base Lambda. Cool. Okay, so no more tail latencies due to garbage collection anymore, right? So if you're profiling your garbage collection, this is very useful tooling because now everyone gets garbage collection. So tail latencies completely disappear because every latency is now a tail latency. So I can do stuff before the process starts, which is really handy, right? But it doesn't really say anything about doing anything in the process. So that's all well and good, but let's keep that in our back pocket for now because that's going to come into what we're going to be doing a little bit later on. So then I want to bring us to Curse 3, which is all about logic in extensions. So I haven't been entirely honest. What actually happens is we have AWS that calls our Lambda API. Our Lambda service instantiates our container. Inside our container, we've got our wrapper script that instantiates our runtime. Our runtime runs our code. But we can also have this stuff over to the side here, right? So we can also run stuff as a sidecar to our code. And this is kind of limited in what it can do because it's got this limited API that it can talk to. It doesn't talk directly to the events API, sorry, the invocation API. It talks to the events API. So you can get stuff about when events were invoked and all of that, but you can't actually get the event itself. So what we can do is, well, why limit our logic to our deployed function, right? When AWS gives us all of these new and exciting, interesting places that we can possibly put it. So here we go. We've got a hello world function that is written in Rust. So all we do is from the body, we get the name. If we have a name, we format a string that says hello whoever. If not, we return hello world, and then we return a response, either status OK and our JSON response. That's right, it was actually a Rust talk all along, right? I left that part out at the start, but yeah, low-level languages have always been a passion of mine, so it has been a Rust talk all along. So if we put our logic in Rust, we can then call that logic from our actual Lambda function. And what that looks like is something like this, right? So what we've done is we've created a Rust extension. That Rust extension starts up when our Lambda starts. And then what we've configured it to do is that Rust extension will actually instantiate a local web server, just local to the Lambda function. And so all we're doing is in our actual Lambda function, the actual deployed code that AWS is running, all we're going to do is talk to that local web server on the path hello world, send it a post with our body, which is our name and our event.name property, and then all we're going to do is proxy through the response that we get from our web server as a text response. So let's prove that model now. There we go, extension hello world.js. So here we go, exactly the same Lambda function, except there's no hello world logic in this Lambda function at all. It all exists in the deployed web server on the Lambda function. So I've got one called hello Aiden here. I assume that's got my name in it. There we go, hello Aiden. As you can see, the duration isn't great. It takes a little while. Oop, I didn't mean to deploy that. Let's run it again. Hopefully it runs a little bit faster. There we go, 168. So we've put our logic in an extension, but it's still not very fast. It's still not as performant as it is running our logic directly, right? So even though there's new and exciting places to put our logic, that doesn't mean all of our logic should go there. Now, I want to raise an interesting point, right? Like, what happens if we take everything we've just talked about and wrap it into one really big cursed Lambda function? Like, what is the most cursed thing we can do with Lambda? And so that brings us to curse 4, which is dynamically modifying invocations on any runtime or architecture, which is a bit of a mouthful, but it's good fun. So how did I end up here? I originally gave a talk at HashiTalks, and it was basically about this, right? Normally when you run a Lambda function, you've got your Lambda code, you might have Amazon API gateway further upstream, you might have a database further downstream, and then in your Lambda layer you might have all of your libraries and all that sort of stuff, which is really cool. But what I really wanted to do was I wanted to have a way to add security by default to these Lambda functions. And so rather than getting a developer to, at the top of their Lambda function, say, do authentication or something like that, I wanted something that was a little more resilient. I wanted to make it so the developer didn't need to remember it. Instead, if they didn't want security, I wanted them to have to think about actively removing that security. And so I sort of built this solution based on some stuff I'd seen New Relic do about instrumenting Lambda functions. And basically what that was when the Lambda function was deployed, we did this. And we actually put our Lambda function handler inside our Lambda layer, and then our Lambda layer called our Lambda code. And that way we could dynamically wrap anything that was built in our Lambda code with functionality from our Lambda layer. And so, yeah, that was really cool and really interesting, but it was sort of limited, right? So it was runtime dependent. You had to have the correct runtime and a Lambda layer that worked with that particular runtime, right? It was fragile. Every time something changed or a library was updated or a Node.js version changed, you might have to rewrite your layers and then redeploy them all, and of course it becomes this whole thing which is difficult to manage. It was also kind of hacky because who puts their handler in their Lambda layer? Not the best place to put it, but it worked, and you could also technically inject modules via mvars, which made the functionality work to inject our handler, but is also sort of worrying from being able to inject other things, right? So what's the alternative in this scenario if we want to do a similar sort of thing, but don't want to expose ourselves to all of these sorts of risks, right? And so I realized that from this slide, there was a bunch of stuff here that I didn't like about it, but I couldn't get rid of all of them. I really had to work out which one of these I could put up with and which ones I wanted to get rid of. So the alternative was doubling down on kind of hacky, right? So this is where it sort of gets a little bit dicey, a little bit weird, but it still works. Well, I haven't been entirely honest, right? Remember how I said that our extension could only talk to the events API and get events about invocations and stuff like that, but it couldn't access the actual invocations themselves. What if we did this? What if instead we put our extension between our runtime and Lambda, and then in our wrapper function, we tell our runtime that AWS actually exists inside our extension, and then we proxy all of our code through our extension to the AWS Lambda runtime API. So and then any architecture is kind of cool as well, because we're looking at running extensions of binaries, right? So these are Rust binaries that we've created. And the thing about, of course, compiling these things is when you choose a Lambda runtime, Lambda's compiled that runtime for that particular architecture, right? But we don't have that luxury. So if you're using ARM64 or x86 64, then you need a different binary for each one. But this is one of the cool things that I found in the AWS documentation was you can actually do something like this, where all you do is you find out what architecture you're running on, and you compile two binaries, so one for ARM64 and one for x86-64. And then you launch the version of your extension that corresponds with the current architecture. So that's really cool. And of course, I've got unsupported architecture down there, just in case someone does something weird like RISC-V. But yeah, so we can run these sort of sidecars, right? And any runtime is the other question, right? So far I've showed you things that have existed in either we've sort of wrapped Node.js, or we've put an extension in, or it's been dependent on what's been running. But can we decouple ourselves from being runtime dependent in this scenario, right? And so because the Rust SDK for AWS is GA, we can write a whole bunch of stuff that interacts with AWS services, and then these services, of course, we can do basically anything we want in AWS with the Rust SDK. So this is the first part of the extension, right? What we've got is we've got a route, and all we're doing is anytime we get a request that looks like it's meant to go to the runtime API, we intercept it and send it to our own getInvocationNext function. And so what we have in this getInvocationNext function, I haven't put the whole function just for brevity's sake, but all we have is we get the name property from our body, and if we have a name, then we return the name JSON, or we send JSON format, whatever it is, and Rust. And then if we don't have anything, then we just send an empty response through, and away we go, right? So if we have a name property in our body, we'll change it. If we don't have a name property, the body just gets proxied through as it is. And then what we do is this is our wrapper script, right? So if you try and add AWS Lambda runtime API as an environment variable in the actual Lambda console, then Lambda will say, no, don't do that. That's a bad idea. And I agree, it is a bad idea, but we're going to do it anyway. So what we do in this wrapper script is we just set the environment variable ourselves, AWS Lambda runtime API, to our local Lambda function, so to our local Lambda extension, and then we exec the runtime as normal. So we now have arbitrary control over the interaction. And so going back to our first example, right? Our first example was just a very simple hello world, right? So we have a handler, and we just return a response with our body hello event.name. And so let's prove out our model, right? Let's see if it all works when we put it all together. Proxy hello world.js. So just to show there's no funny business going on, this is our Lambda function here, hello event.name. If I go to the test page, the name is Aiden, so we're expecting hello Aiden from just the code that's deployed, not including the extension. And if I test this, fingers crossed, hello Aiden and Rust. So we've intercepted the call as it went between AWS and our actual runtime. And the cool thing about this is if you look at that duration, that is actually significantly better performance than pretty much anything we've seen so far, right? So we're actually not incurring a huge performance overhead in doing all of this sort of stuff. So it unlocks really sort of interesting possibilities that we wouldn't have had otherwise. So let me go back to my slides. Yeah, I did say any runtime, right? And so far I've only shown you Node.js, so who knows, I could have written something in Node.js and we don't have any way of knowing, unless I actually wrote it in Python as well. So that's what I've done. We have a handler that is in Python and just returns exactly the same thing. We've got our status code and our JSON body with hello event name. So we can send exactly the same event through to Python. Now, the other thing I want to call out here is if I go to configuration. It's been a while since I've actually had to use the terminal. There we go. Architecture for this one is ARM64, right? So I've been running Node.js on ARM64, just because if we're going to do a different runtime, why just change the runtime when we can change the architecture as well, right? So let's go Python x86 64. So jumping in to proxy hello world pi, we've got exactly the same thing. Once again, no cheating going on. If I open up our test function, we've got name here is test. And if I test this, we'll get, hopefully execution succeeded, hello test and Rust. So this is really cool, right? Because it's not limited to just that particular runtime, and it's very cross-compatible with anything you want to deploy on Lambda. So we've done it in Python, we've done it in Node, we've done it on ARM, we've done it on x86-64, and this is all one Lambda layer as well, by the way. It's not like I'm switching out Lambda layers halfway in between. So if I jump into code, you can see we've got our layer down here. I've only registered as compatible with Node.js, but it does work with Python, as we just saw, because this is the Python function. It's compatible with both x86 and ARM64, and yes, it did take me 56 tries to get this right. Please don't laugh at me. So it's a really interesting sort of concept, right? That's the slide I was meant to have up before I showed you the Python version. Cool, so we've managed to do this, right? We've dynamically modified invocations on any runtime or architecture. So the first 3 cursors were maybe a little bit of a red herring. They were setting the groundwork for this final pattern. And so there's some really cool implications of this, right? So we're not only now limited to stuff we can do in managed services and stuff like that, we can put anything we want in between the Lambda API and our function. So if you want to do defense in depth, if you want to make sure that you're validating like a JWT token, or if you've got something that you want to check for SQL injection or anything like that, and you want to do it at the Lambda function layer rather than at a WAF layer or something else, of course, there's good reasons why you should do it at the WAF layer and at every layer, but if you want to check that at every layer, you can do defense in depth through this sort of pattern, right? And any of those sorts of strategies you can write in Rust and deploy to any architecture and any runtime. Tracing and monitoring is another cool one, right? So a lot of instrumentation for tracing and monitoring comes through in either as libraries that you need to import and stuff that you need to add in yourself, or you need to do specific types of logging and stuff like that, and then the extension of the Lambda function talks to the Lambda logs API and then exports those out to your third-party tracing and logging provider and monitoring provider. But because we can intercept the events themselves directly, we can actually do all of that without integrating any libraries and completely transparently to the developer, right? And then, of course, there is one other really good thing that this pattern is useful for, which is request enrichment. So if you've got, like a user string or something like that in your headers, or you've got any sort of information that you want to enrich or add additional context to, then you can do that and provide that through to your actual Lambda function. And the last thing that it's good for, and my primary purpose, is making fun PowerPoints, right? So, if you want, it's a fun topic to play around with, and I wouldn't recommend using it necessarily in production, but it's a pattern that's useful to know exists, right? And our idea wasn't to give you necessarily tools to take away and go use tomorrow, but our idea was that we wanted to test the bounds of a system, and we wanted to use that test to build mechanical sympathy for the underlying systems that we use every day. So yeah, hopefully I've achieved that. I did need to go a little bit faster, but I think I've went a little bit too fast now, so we'll have plenty of time for questions. But yeah, if you've enjoyed the talk, this is my LinkedIn. Feel free to connect, and I'll open up the floor to questions. If anyone wants to have any questions about the code or about my sanity, feel free to ask away.
Thank you, Aiden. It's time to give questions from the floor. Just raise your hand, and the mic will come to you.
Is there an advantage doing it this way for event enrichment compared to putting another Lambda in front of it?
Yeah, so it really depends the way your Lambdas are set up, right? So if you're doing request enrichment through something like API gateway, and your API gateway is awaiting response, then whatever Lambda is doing the enrichment is going to be running for the same time that it takes for the Lambda to do the processing actually runs, right? So by chaining 2 Lambda functions together, you're paying for twice the compute, even though only one piece of compute is running at a time. So there is an advantage there. You could do it technically like in any of the, it depends what sort of request it is. Like if it's a cognito request, you could do it in like a pre-token generation hook or something like that. But for API gateway stuff, it's kind of handy to be able to do it all in one because you're not doubling up your compute by chaining lambdas together. So it's a cool way, but yeah, you could solve it in different ways as well. Same scenario. Any other questions? No?
Well, if we don't have questions, let's give a big applause for Aiden.